Let's go.
Cool. Dear listener, I'm coming to you from a dense, wet rainforest in far northeastern Australia. It's February, the middle of the wet season. I'm out here on an early, rainy morning, following my trusty forest guide, Andrew Ford, deeper into the forest.
So there's a few rules in the rainforest. Number one, you're never ever in a hurry.
Okay.
Unless a pig's chasing you, or a cassowary looks angry. Otherwise you'll end up on your ass or your face.
Are there pigs in here?
Yes. Yeah, not your German boar, your feral pig.
We're stepping over slick roots and rocks and a thick carpet of wet leaves, ducking under low branches, scrambling over rotting tree logs, and trying our best to dodge the long, jagged vines that crisscross our path.
So these things, bad. See, they grab hold of you, so they actually tear your flesh.
Oh, what is it?
Thing called wait a while, or calamus, lawyer cane.
If you have ever been trekking through a tropical rainforest before, you'll know that it's not all butterflies, birdsong and waterfalls. More often, it's mosquitoes, mud, sweat, stinging plants, and, in this one, flesh-tearing vines and blood-sucking worms. What about the leeches?
There's lots of them. They don't mind us. We have the paperbark satin ash. So satin ash because it's...
Andrew Ford is a botanist. He's been coming to the rainforests in this region for decades. He knows them like the back of his hand. The name of every single plant and every single tree, every bird call we hear and every critter we encounter, many of which he has nicknames for.
The Arnold Schwarzenegger of rats, the white-tailed rat, which is actually the size of a possum and has got an attitude of a tiger.
And yet, the reason that I'm following him is because there's been a monumental shift here that even he didn't notice.
I was surprised because I go to them a lot and you just don't see that kind of a change.
This is Living Planet. I'm Charlie Shield. Today, we're going deep into the rainforests of far North Queensland, Australia, and back out again to find out what is changing here and why it matters for the global carbon budget.
Frankly, we were kind of shocked.
That's Hannah Carl. She's a forest scientist.
I'm based at the Hawkesbury Institute for the Environment at Western Sydney University in Australia, and I work on trying to understand how forests respond to climate change and what that means for us in terms of what forests do for us and the intrinsic value that forests have.
For the last several years, Hannah and a team of scientists, including Andrew, have been working on understanding how the moist tropical forests in Australia's northeast are responding to climate change. Recently, they published their findings in the journal Nature.
What we found looking at the moist tropical forests in Australia's far northeast is that the woody biomass in those forests, which is a really important and large store of carbon, it used to act as a carbon sink, which is what we expect. It means that year on year it takes up more carbon than it releases.
Woody biomass, by the way, is basically the solid wood of trees, their trunks, their branches and stems.
So it used to act as a carbon sink and now has changed to being a net carbon source because of responses to extreme climate from human-induced climate change.
The trees here are dying twice as fast as they used to, faster than they can be replaced by new trees. And that means that more carbon is being lost to the atmosphere than can be absorbed by new trunks, new branches and new stems. Forest scientists have long considered the intact rainforests in northeast Australia to be reliable, sturdy carbon sinks. They're some of the most carbon-dense ecosystems on land, alongside the rainforests in the Amazon, the Congo Basin, New Guinea and Borneo. And unlike those rainforests, these Australian ones aren't threatened by deforestation. They haven't been logged for more than 3 decades. They're tree-dense, biodiverse and seemingly resilient. which is part of the reason that Hannah and her team were so shocked by their findings.
This is not a small shift in the balance. This is essentially a complete reversal when we look at the numbers. So that took a while to come to terms with, and we were checking and rechecking and just trying to think if there was anything systematic about the data or our approach to the analysis that could be giving an illusion that this was the pattern, because it was a bit hard to conceive.
What's more, this reversal wasn't even all that recent. It occurred around about the year 2000.
It's about 25 years ago.
Hannah and the team reached this conclusion using an extraordinary long-term dataset dating back to 1971, where the same patches of forest had been tracked over and over across decades. What the data revealed was a gradual, steady change, driven by a changing climate.
We have higher losses of biomass in periods when we have more extreme temperatures, but also drier atmosphere and also basically drought extremes. And we know that all of those extremes have been increasing through time.
The kind of tree species that live here are used to warm, wet conditions. Sauna-level humidity is just how they like it. As climate change accelerates, they're being subjected to more extreme highs and lows, as well as drier air. That, plus other stresses like pests, pathogens and water scarcity, are combining to push trees beyond their limits.
Trees don't die just because of one thing. Trees mostly die because they've been exposed to perhaps 4 or 6 different stresses. It's probably not that it's just so hot that it's cooking the tree, so to speak. It's probably that it's affecting the baseline capacity of the tree to deal with the other stresses that it's experiencing.
Increasingly severe cyclones are also having an impact here, wiping out masses of trees when they roll on in, contributing to tree death and weakening the forest's ability to store carbon. In fact, when I was exploring the forests with Andrew, he kept pointing out large swaths of dead trees that were killed by Cyclone Larry back in 2006.
So after Larry, you had big light gaps, but also you had a lot of leaves stripped out of the canopy. So, you look up there now, if you can imagine.
But apart from cyclone damage, on the ground, the study's findings are pretty hard to reckon with.
It is surprising, and I was very surprised at the results, to be 100% honest.
To be fair to Andrew, this shift is not something that you can really see. Looking around, nothing appears that wrong here. In fact, standing in one of these forest plots, mud underfoot, mosquito on my cheek, I'm struck by just how alive it feels in here. Full of noise and activity, of rot and renewal. Everything you would imagine a healthy forest to be.
You got all different size classes or demographics of particular species or individual species, from little things and seedlings to forest giants. And so that tells you that that suggests that the forest is healthy, because things are just turning over all the time.
And that is the strange thing about this switch. The forest looks much the same, but the data tells a different story. This kind of shift is not just happening in Australia. Scientists have also documented a weakening of the Amazon rainforest's ability to store carbon. Rising heat, drought and deforestation have also flipped parts of the Amazon to a net carbon source. But something else is happening there too. Higher levels of atmospheric CO2 appear to be acting kind of like a fertiliser, encouraging more tree growth. And that is offsetting some of the losses.
And so on balance, you've got in the Amazon a decline in the total carbon sink strength, but still a net carbon sink.
For some reason, however, this balancing effect is not happening in Australia.
So we know that when trees are dying faster, more carbon is lost from the system. What we expected to find, though, was a sort of counterbalance to that with increasing tree growth because of higher levels of carbon dioxide in the atmosphere. So what was really surprising, I think, was looking at the other part of that carbon balance equation and finding that that was not remedying the situation in the way that we expected.
Researchers aren't totally sure why this happens in one place and not in the other. But Hannah says they suspect it's due to the difference in the availability of soil nutrients and that more research is needed. So if carbon dioxide is invisible, how do scientists actually measure a shift like this? Well, they measure the trees themselves.
So this is the edge of the big plot, as we call it, the turn plot. So 25 hectares of rainforest that we mapped out, ID'd everything, measured everything, heighted everything, coordinated everything.
Andrew's showing me one of the long-term forest plots where data is collected. 20 of these across a massive swath of forest were set up in the 1970s and the early 80s. Each 25-hectare plot is carefully mapped. Every tree above a certain size is numbered, identified and measured.
So if you were looking for this particular tree, hectare 23,565, and you're coming in from this way and you saw the paint on this tree, you'd say, oh, we're really close, it must be here. Whereas if there was no paint on it, you're just looking for another tree. So it just gives you a visual.
And this is when I learn why Andrew's rainforest outfit, from his drawstring bucket hat to his bush boots, is splattered from head to toe with yellow paint, as if he were a painter who'd lost his way in the woods. On measuring days, Andrew carries a barrel of yellow paint into the rainforest to mark the trees in the plots.
In the 25 hectares here, there are just under 24,000 stems over 10 centimetres diameter. On a world stage, that is extremely high. So that's one thing our rainforests are renowned for, is the high stem densities.
Lots and lots of trees.
Lots and lots of trees. So people who are used to like Amazonian type of forest, or what they see on TV, or Malaysian Bornean forest, very different.
The work is slow and methodical, and some plots take days to reach.
It's kind of extreme, and people do it because they understand just how valuable the data are and what these kinds of long-term monitoring efforts tend to tell us about the world that other techniques or more modern, more accessible technologies don't have the power to.
For 50 years, scientists have returned here again and again, tracking which trees grew, which died, and which new ones appeared. And it's from those measurements that they can calculate the above-ground biomass, basically the total mass of living trees in a given area. From there, they figure out the carbon storage capacity.
So when we say that the above-ground biomass has become a net carbon source, what that means is when we add up all of the growth of the trees in a patch of forest and how much carbon is gained through that growth, and then we minus away all of the carbon that's lost each year because of the trees dying and turning over, the sum of those gains and losses has switched, the balance has switched in favour of net emission or net loss of carbon.
So what's the bigger meaning of this finding? Well, for starters, it suggests that this all-important patch of wilderness is not absorbing as much fossil fuel pollution as we expect it to. And that could be a problem for the way we do some climate math.
We have emitted already 2 trillion tons of carbon dioxide from burning fossil fuels into the atmosphere. And about 1 trillion tons is still floating around up there. Most of that CO2 will still be there in thousands of years. And we estimate that we only have a few years of emissions before we'll cross the 1.5 degree C threshold as a global average, and maybe another 20 years of emissions before we cross the 2 degrees C threshold.
Rob Jackson is a climate scientist at Stanford University.
And I specialize in forests and ecosystems and climate.
He's also chair of the Global Carbon Project, an international group of scientists working to measure and reduce greenhouse gas emissions. Part of their work involves calculating how much carbon dioxide humanity can still emit before we cross critical warming thresholds. That is called the global carbon budget.
And you have to bear in mind that we're emitting 40 billion tons of fossil carbon dioxide pollution a year. And the infrastructure that we have on the Earth, power plants, steel plants, cars, lasts for decades. So the long-term embedded emissions of the infrastructure already on the Earth take us well past 1.5 C and up to and possibly past the 2 degrees C, just if we keep using the infrastructure that's already been built on Earth. So we're dangerously close to both thresholds.
It sounds like a small difference, half a degree of warming, even every 10th of a degree of warming. But when it comes to an increase in average global temperatures, every fraction is predicted to change our lives dramatically. It increases the frequency and intensity of extreme heat, drought, flooding and storms, accelerates sea level rise, and disrupts planetary systems that keep the climate livable. For many decades, forests, soils and oceans have helped slow that warming by absorbing about half of the carbon dioxide we emit through fossil fuel pollution.
If those sinks went away, atmospheric concentrations of carbon dioxide would rise twice as fast as they do today for the same unit emissions.
Since carbon dioxide is invisible, it might be helpful to have a visual here. I asked Rob to help us picture this.
Think of the atmosphere as a bathtub or a large bucket, and we can put so much water into that bucket before it starts to overflow. We have to take into account how much water goes in and also how much water comes out of that bathtub. And the loss of forests in these other sinks means that carbon dioxide and methane and other greenhouse gases wouldn't be removed from the atmosphere as fast. So that has the same effect as increasing emissions, because the balance of CO2 in the air is what goes in and what goes out. And most of what goes out through plant photosynthesis and absorption by ocean water and phytoplankton. And we don't want that to go away, but we're in danger of losing that strength, that sink strength.
More and more, scientists are seeing signs that those sinks are weakening. Rob and his colleagues track carbon dynamics in forests across the Amazon, Scandinavia, and the United States. There too, they're observing climate change undermining the forest's ability to store carbon.
We have seen greater and more extensive fires, more intense fires. And that disturbance affects forests too, because of course, when a burn comes through, you free carbon into the atmosphere. Often the forest regrows, but in all cases, the forest necessarily can't regrow everywhere. And I think that's what we're starting to see in the Amazon through like the last 2 years, where we had the very intense El Nino, where the Amazon was not just hot, but hot and dry.
A warmer climate is also allowing insects and pests to set up shop in new regions that were once too cold for them to survive. Places where they can grow faster and survive for longer.
The intersection of sort of droughts and stress on forests with increased beetle outbreaks has led to the loss of large stretches of forest, particularly across northern US and Canada, to some extent in Scandinavia too. I think it's also important to point out that it's not one factor working alone. It's all of these factors working together. Droughts, beetle outbreaks, increased fire frequency in some places. They strengthen each other and reinforce each other where they co-occur.
And even though previous research has shown carbon dioxide stimulating tree growth in the Amazon, Rob says that there is a ceiling on that effect.
I've worked on many experiments over my career where we have exposed forests to increased carbon dioxide concentrations. And one of the most interesting findings in those studies is pretty intuitive, really, and that's that carbon dioxide is a food, it's a substrate for photosynthesis. But if plants don't have enough water, and particularly if they don't have enough nutrients, nitrogen, phosphorus, potassium, compounds like that, they can't take advantage of the extra carbon through photosynthesis. So essentially, they're a bit like people. You have to have vitamins as well as food to grow a healthy body, and trees and other organisms are the same. If they don't have enough nutrients, then their response to elevated carbon dioxide decreases or is quite small.
And all of this raises a critical question. If forests are not absorbing as much carbon as we expect them to, and as much as climate models assume they will, what does that mean for the emissions targets that governments have set to avoid ever more dangerous levels of global warming?
In general, policymakers plan for what's happened in the recent past. And the recent past for us in the last 30 or 40 years has been to have substantial sinks in the oceans and forests. Well, I think most scenarios and most policymakers assume that those sinks will continue. And it's an open question in the scientific community. I believe there's increasing evidence that they will slow.
In other words, the world's carbon budget might be smaller than we thought.
Part of the reason is that as we keep adding more and more carbon dioxide into the atmosphere, the incremental benefit of that carbon dioxide for a plant or a phytoplankton in the ocean decreases with more and more as you add. The extra bit on top of a lot is less useful than the extra bit on top of a small amount. Most policymakers and scenarios are banking on these sinks to continue, and may mean that we're underestimating the amount of mitigation or emissions reductions that we need to do.
In absolute terms, the loss of the rainforest sink in northeast Australia is not going to blow our global carbon budget out of the water. What's important and unsettling about this science is what such a quiet reversal signifies.
It's a very important signal, and we would say like an early warning signal that there is a change afoot. But yeah, these are like healthy, intact forests, still very biodiverse, still very structurally complex, very high biomass. You wouldn't look at the forest and think, oh, we have a problem here. But yeah, we would expect the change to become more apparent through time.
I ask Hannah, is this kind of thing reversible?
There are some changes in ecosystems that are permanent in the sense that we don't seem to be able to go back to exactly what we had before some kind of stress or change was imposed. But in terms of this carbon balance, like, could we go back to being a net carbon sink? The answer is yes. We think so.
Hannah says ecosystems can switch back and forth between carbon sink to source to sink again. In fact, scientists have observed this very thing happening in the Amazon, where an extreme drought turned it into a net carbon source in 2023 before better conditions returned it to a net sink. This does suggest some elasticity when it comes to how ecosystems store carbon. But the case in Australia is distinct.
So in this case, what we see is this long-term trend of declining carbon sink capacity, and now to the point of being a net carbon source to the atmosphere. And that's because of a long-term shift in the climate conditions that means currently it's less favourable than it was 50 years ago. But if those climate conditions changed, or if there was some other way of perhaps supporting the functionality and the health of the forest that could stimulate tree growth or minimise tree mortality, then there's every reason to think that we could have this above ground biomass working as a carbon sink yet again.
And that brings us back to the underlying cause: too much carbon dioxide in the atmosphere, driven primarily by humans burning fossil fuels.
I mean, it might just feel so pie in the sky given where we are kind of in our trajectory at the moment, but we could reduce atmospheric carbon dioxide levels, and that would support the carbon sink capacity of the forests, we would think, based on our current expectations and knowledge of the system.
Kind of interesting here. Couple of unhappy trees here.
Unhappy?
Because they're dead. You can see what happens when things die and fall. They start decaying, and even standing trunks or standing stumps like this slowly get decayed out by fungus in particular, and insects, and then birds come in looking for the insects and rip it out. Yeah, particularly birds, like rifle birds, will come in and try and grab worms and bugs out of them. And it's only the big, tall, standing deads there. You just see all the base of the tree has got frass all on the ground. So where all the borers have got in. Just over there, so that's another.
Death is not unusual here. It's the basis of the ecosystem. Something dies and something else grows. Life turns over. As American author Ursula K. Le Guin wrote at the turn of the century, the forest is forever because it dies, and so it lives. And perhaps that's partly why this shift has been so difficult to see.
You do see dead trees, you see fallen trees, but you just assume that any losses of those particular trees, big or small, is being picked up by the other trees.
And though Andrew isn't alarmed by the findings, they do give him pause.
It certainly doesn't keep me awake at night, but it's something that I think all people like myself do think about. And, you know, in the back of your mind, you often think, you know, hopefully I don't get to see any of these changes in my life, but it's always in the back of your mind that maybe it could happen fast enough that you start to see the front edge of it in some places, and not everywhere will be affected, I assume, at the same rate or the same time. And so you may start seeing a signal somewhere quite unexpected.
Andrew will keep returning here, compass in hand, pot of yellow paint under his arm, again and again, measuring the trees, recording the old, the new and the dying, paying attention to the forest in all its forms, as it shifts and as it changes. This episode of Living Planet was reported and produced by me, Charlie Shield. It was edited by Neil King. I did the soundscaping, and our sound engineers were Michael Springer and Simon Burkhan. Thank you so much for listening. You can send us your feedback in email form to livingplanet@dw.com. Or you can leave your comments for us on Spotify, Apple Podcasts, or YouTube, or wherever you listen to Living Planet. Nowadays, you can also record little voice notes for us at speakpipe.com/livingplanet. And who knows, maybe you'll hear yourself on the show one day. Living Planet is produced by DW Studios in Germany.
Where is the most disturbing place that you've ever found a leech?
Well, in my eyes,
You've had leeches in your eyes.
I've had them a few times in my eyes.
How do you deal with a leech in your eye?
You don't deal with it, you let it happen. You just enjoy the experience, and usually after 30 minutes you feel it wriggling back out, and you never pull a leech out of your eye because you'll invariably damage your cornea or your iris. You get a leech in your eye, you leave it there and enjoy the experience if you can enjoy it.